Hey guys, in this video we are going to look at the forces between parallel conductors. Now if you guys just want to see how to perform calculations on 3 or more conductors, have a look in the description down below and there should be a timestamp there for you if you want to skip to it. Anyways, let's get started. So to calculate the force between current carrying conductors, we have to look at why current carrying conductors produce a force on each other in the first place. So if you learnt from module 4 that a current carrying conductor, that is a wire with electricity flowing through it, let's say that the current is pointing upwards, is always going to produce a radial magnetic field, a circular magnetic field that is determined by the right hand grip rule. Okay? And the way we denote that on a 2D piece of paper is by drawing dots and crosses. So if you guys use your right hand grip rule, you can see that if I point my thumb upwards, my fingers are going to point towards me or out of the page on the left hand side and into the page on the right side. Okay? So out of the page on the left hand side and into the page on the right hand side. So that means that when I have another conductor placed beside it, depending on the direction of the current, that conductor is either going to is going to be under the influence of this magnetic field. Okay? So let's say, for example, that we have a conductor with a current in the same direction, so both moving in the same direction. You can see how this conductor, the second conductor, we're going to call it conductor B, right? We'll call this A, we'll call this B, is going to experience a magnetic field going into the page, right? You can see how it's experiencing that magnetic field. And so from lesson 1, which you guys should know as the motor effect force, a conductor inside of a magnetic field is going to experience a force given by the right hand palm rule, right? So from the motor effect, we know that the fingers represent the magnetic field, the thumb points in the direction of your velocity or the current, and as you can see, the palm is going to point towards the left. And similarly, if you do the same thing for this conductor, right? If we look at the magnetic field produced by the right conductor, so conductor B, thumb points upwards, fingers curl out of the page on the left hand side and into the page on the right hand side, you can see now how conductor A is going to experience a magnetic field coming out of the page. You can see that here, right? The magnetic fields are coming out of the page. So when we go ahead and calculate the forces, thumb points up, this time fingers point towards you or out of the page, and as you can see, the palm is going to push conductor A towards conductor B. And as you can see, as a result, right, when we have two parallel conductors, both in the same direction, it is going to experience a force of attraction. Attraction, okay? And you can also do this for opposite direction conductors as well. And that way you will see when you do this, right? I'll just quickly do it for you. So actually don't worry about it. But basically, you'll see that you get a force of repulsion. So I'll let you guys figure that one out, but you apply the same techniques and you'll get this this result, okay? So you guys can have a go and you can determine that. But the TLDR here is that if I have currents in the opposite direction, we will actually get a force of repulsion. All right? So once you understand that, we can then go ahead and look at the equations that we can use to determine the magnitude of these forces. So just remember for me, guys, if I have current in the same direction, you're always going to have a force of attraction, and if you have current in the opposite direction, you'll have a force of repulsion. And that's why these conductors push and pull on each other. So if I want to now calculate the magnitude of these forces, right, F here, F there, we simply have to just use the equation F1L is equal to mu naught I1, I2 divided by 2 pi r. Okay. Now here, L is the common length, the length of these conductors, L. Mu is your magnetic permeability, right? It's a constant. It's 4 pi times 10 to the negative 7. It's in your data sheet, so you can check that as well. And then I1, I2 is just the current of conductor A, conductor B. And lastly, R is the distance of separation between these conductors. Okay, so just remember, this is the equation that we use. And the rule is, if you have current in the same direction, we get a force of attraction. If we have current in opposite directions, we have a force of repulsion. Okay, so let's have a look at an example here. So example number 1, 2 parallel wires length 2 meters apart are separated by a distance of 15 centimeters. Okay. Yeah, okay, sorry, I was just reading that a little bit incorrectly, but okay, cool. So we have two lengths or two conductors that are 2 meters long, right? 2 meters long, separated by a distance of 15 centimeters. That means that this distance here is 2 meters, that's the common length, and we have a distance of separation of 15 centimeters. So that's going to be in SI units, don't forget SI units, 0.15 meters, okay? Now the question tells us that current A, wire A, carries a current of 5 amps upwards. I1 is 5 amps. And I2, so current in wire 2 is 8 amps downwards. Okay, so I2 is 8 amps downwards. Whoops. 8 amps. And you can see it's going in the opposite direction. So it's downwards. Cool. So we have these two conductors where one is going up, one is going down. First of all, first thing you want to think about is this a force of attraction or repulsion? And the answer is obviously going to be repulsion, right? Keep that in mind. Cool, so we're going to draw that out where we'll have a force of repulsion. Like so. All right. Calculate the magnitude and direction. Direction we already know, that's going to be repulsion. So we'll just quickly write that down so we don't forget. Of the force experienced by wire B, okay? Cool, so they want us to calculate the force, net force on wire B. So to find the force, we just use the equation F on L is equals to mu naught I1 I2 over 2 pi r. Okay, now I'm not going to waste your time. It's quite trivial. The force is equals to mu naught, which again, you guys can just plug it in yourselves. That's going to be 4 pi times 10 to the negative 7. It's in your data sheet. I1 we said is 5, I2 is 8. Divided by 2 pi r. Now don't forget L, right? L is the common length. They're both 2 meters, so we just multiply by 2. Okay, cool. Equal to dot dot dot. I'm not going to waste your time. Like I said, you guys can plug it in yourselves. Newtons. Now are we done? No, because remember, force is a vector and we need to have a direction. What's my direction? Is it repulsive? No. Remember, the question asks for the force experienced by B. You can see here A and B, right? If I say repulsive, what does that mean? That's not giving me a direction. You have to say either to the right in this case, because we drew it out like that, or a better way is away from A. Okay, does that make sense? You gotta make sure to include the direction. Now here, yes, we know it's a repulsive force, but more specifically, if they're asking for the direction of B, B simply just moves away from A. Okay, make sense? Cool. So remember, when you're trying to calculate these forces, number one, just calculate the force, the magnitude of the force, and number two, look for the direction. If they are in the same direction, it's attractive. If they're in opposite direction, it's repulsive. Now, moving on to a harder example, example 2. How do we deal with 3 wires? So when we have 3 different wires, the problem becomes a little bit trickier. Why? Because with 2 wires, we only have to deal with either an attractive force or a repulsive force. But when it comes to 3 wires, what you will notice is that when you have 3 wires, there's actually going to be 2 pairs of forces for each wire. So let's say, for example, this is A, this is B, and this is C. Because the force shown here represents the forces between 2 pairs, right? When you have 3 wires, you actually have 3 different pairs. For example, AB is going to apply a force onto each other. AC is going to apply a force onto each other, and BC is also going to apply a force. So there's actually 3 pairs, okay? Which means that when I look at the total forces, how many forces are there? Well, there's the interaction between A and B. That could either be repulsive or attractive. We're just going to say repulsive for now, just to show you. You know what, we might as well just give some directions. Okay, we'll say current here is upwards, we'll say current here is downwards, we'll say current here is upwards, right? Cool. A and B being different directions, that's a repulsive force, okay? But there's also going to be an interaction between, for example, B and C, right? B and C, which I will use a different color, I'll use black. B and C again is, because they are opposite directions, we're going to have a force of repulsion. And the last pair that we must consider, which I'll use green for, is A and C, okay? A and C are same direction, so we're going to have a force of attraction. So you can see that when you have 3 conductors, you now have 2 pairs of forces for each conductor. Once you understand that, the magnitudes of these forces are still the same. And then you can calculate what the force you want to calculate, okay? So let's do an example. Question 3, we have 3 wires, A, B, and C. So here's A, here's B, here's C, conductor A, conductor B, conductor C. Let's say A, question says 10 amps upwards, cool. B is 5 amps upwards as well, but it is placed 0.1 centimeters to the right of A, so that's 0.1. Like so, cool. And again, SI units. YC is 20 amps downwards, so this is going to be downwards here. Downwards 20 amps. Cool. And again, SI units, so okay, give me 1 second. 0.1. Cool. So 0.1 also to the right of B. Nice. Now what they want you to do is they want you to calculate the net force per meter in the middle wire. So they want you to find on wire B. Okay. So again, I showed you earlier here that there's 6 forces altogether, but we don't actually need to calculate all the forces, right? Why? Because the question only wants the forces on the middle wire. So because they only want the net force on the middle wire, wire B, you only have to consider the forces here. You don't need to consider the other forces, true? So we're only looking at 2 forces essentially. So when we're looking at wire B, how many forces do we have? Wire B interacts with A and C, true? Okay, so A is upwards, B is upwards, that's a force of attraction. We're going to call that F1. B and C are opposite directions, so we're going to have a force of, what is that? Repulsion, right? Now, because it's repulsive, B is going to go to the left and C is going to go to the right. We're going to call those forces F2. So as you can see here, when you look at conductor B, notice how there are 2 forces to the left, true? Which means that if I want to calculate the net force on B, I can just say F net B is equal to, now remember, don't forget, you have to assume a direction to be positive here, because F1 and F2 are to the left. I'm just going to say we're going to take left as positive, all right? Which means, what's the net force on B? It's F1 plus F2. Okay, that's it. Now, all we have to do from here is plug in the forces for F1 and F2. What are the forces? Again, we're just using the equations from earlier, right? The force between current carrying conductors. So F1 is between A and B. So when I plug in the currents, I'm going to plug in the current for A and B, right? So when you're putting this into the equation, you want to plug in the very following. Mu naught. Now I1 is 10, right? Okay. I'm not going to do that. I'm just going to write it out first. So it's IA, because this is 1, this is 2, this is 3, right? The current A, current B, current C. You guys get the point, yeah? Okay, IA, IB over 2 pi R. Also, don't forget times L. Why are we multiplying by L? Because I'm just looking at the net force equation. So because I'm using the net force equation, I'm basically just taking this length L and I'm moving it over to find the force. Okay, so that's why, in case you're wondering why I'm putting the L there. So times L plus, same thing, I'm going to move this over real quick. Mu naught. Now this time it's between B and C, so that's going to be IB and IC. Again, times L all over 2 pi R. So now all you have to do, guys, is just plug those numbers in, and that's going to be your net force, okay? So you plug it in, equal to, now note, actually we'll plug it in. Oops, 10 times 5. 2.1 times L plus mu naught 5 times 20 times L over 2 pi R, okay, which is again 0.1. Now you guys might be wondering, why am I putting in L instead of just putting in 2? Something I forgot to mention is it's asking for force per meter. Because they're asking for force per meter, I need to make sure to divide everything by L, so the L cancels out anyways. And what you're left with is the force per unit length is equal to, the values found here, okay? So it's going to be newtons per meter, okay? So essentially what I'm doing is I'm taking these L's and I'm factorizing it and I'm putting it to the left-hand side to give me the net force per meter. Cool. Okay, and that's it. So, and don't forget, guys, the forces are to the left, so we need to say to the left. Okay, and that's it. So that's how we solve questions involving 3 or more wires. Okay, the rules are the same. If you have currents in the same direction, it's going to be a force of attraction. If you have current in the opposite direction, you will have a force of repulsion. So when you just have more than 2 wires, the difference is that you just need to consider the different number of forces acting on that particular wire. Okay, so that's it for this lesson. Remember, make sure to subscribe if you want more videos, and there's also free notes down in the description. You can find it on our Discord community. Cool. All right, so that's it for this lesson. I'll see you guys next time.